Welcome to the 2026 February 1st week edition of Biomanufacturing and Fermentation Technology. I'm Prasad Ernala. This week, long-held assumptions in fermentation quietly broke, around sterility, scale, and strain robustness. If you work in biomanufacturing, these shifts matter. Let's dive in. The upstream inflection. Biological and process assumptions that just broke. This week, a core assumption in fermentation science quietly stopped being true. The assumption that high-titer lactic acid production from industrial waste streams requires both nutrient supplementation and sterile conditions to protect yield. That assumption has guided facility design, media formulation, and operating philosophy for decades. And now, it has been directly challenged. The main story. In a study published February 2, 2026, researchers reported an engineered Bacillus licheniformis strain, OP16-2, capable of converting corn steep water, an unrefined industrial waste stream, directly into lactic acid. No nutrient supplementation. No sterilization. And critically, no collapse in productivity. The process ran under thermo-alkaline conditions, specifically 55 degrees Celsius and pH 8.5. Under fed batch operation, the strain reached 180 grams per liter lactic acid in 48 hours, with a yield of 0.95 grams per gram of substrate. That is roughly a 30% improvement over prior benchmarks under comparable constraints. Mechanistically, this was not a single gene trick. It was systems-level rewiring. Adaptive laboratory evolution was used to drive alkali tolerance, with strong upregulation of sodium proton antiporters and classical heat shock proteins such as GRO-EL. At the same time, intracellular amino acid pools were redirected away from biomass buffering and toward glycolysis and lactate dehydrogenase flux. The net effect was counterintuitive but powerful. The organism became metabolically self-sufficient under stress, eliminating the need for rich media. High temperature suppressed mesophilic contaminants by default, relaxing sterility requirements without antibiotics or biocides. From a process perspective, this is where the shift becomes real. Sterilization typically contributes 15 to 20% of operating expenditure in organic acid plants. Complex media formulations inflate cost of goods by another 20 to 25%. This strain collapses both penalties at once. Pilot-scale validation at 10 liters confirmed shear tolerance and minimal foaming, largely due to the simplified broth composition. In other words, this result survived scale-up physics, not just lab conditions. Why it matters? For founders, this directly attacks capital intensity. Eliminating sterilization infrastructure can remove up to $5 million in mid-scale facility CAPEX. That enables faster pilots, lower burn, and proof of economic viability well before GMP investment. Time to market for commodity biochemicals could realistically compress by 12 to 18 months. For scientists and engineers, this is a blueprint. It shows how flux balancing under extreme stress can decouple growth from production. It also validates the combined use of ALE and targeted genome editing to design strains that tolerate pH and temperature gradients typical of large fermenters or continuous systems. The big takeaway. Non-sterile no longer means low performance. That line just moved. The downstream and scale reality. What breaks when volume and time increase? You can express it in the lab. But can you still recover it after 96 hours at industrial scale? This week's reality check comes from gas fermentation, where elegant lab models collided with hydrodynamics, shear, and mass transfer limits. The main story. During the 2025 to 2026 transition of Global Envirotech's Illinois facility from a 1,000-liter demonstration scale to a 50,000-liter commercial reactor, a core assumption failed. Lab data assumed relatively uniform gas dissolution, with volumetric mass transfer coefficients around 200 per hour. At scale, spatial gradients emerged. Entire zones formed with 40% lower CO and hydrogen uptake, collapsing ethanol titers from 50 grams per liter down to 28. The original assumption was near plug flow behavior. The reality was heterogeneous mixing. Worse, shear rates approaching 1,000 per second induced partial cell lysis. That increased fouling in downstream evaporation membranes, cutting recovery efficiency from 85% to 60%. The fix was not elegant, but it worked. The team retrofitted the reactor with zoned agitation, reducing concentration gradients by roughly 70%. They accepted a 15% yield penalty by lowering dilution rates to maintain cell viability over long campaigns. The result was a stable 200-hour run, not a record titer. This is the lesson. At scale, robustness beats theoretical optimality. In parallel, infrastructure is adapting. BioMADE's new 10,000-liter non-sterile pilot facility, opening in 2026, directly addresses these failure modes. The plant integrates Raman spectroscopy PAT to resolve spatial heterogeneity in real time, with variance reduced below 5%. Soft sensors predict fouling before flux collapse, extending resin lifetimes beyond 80 cycles. Shared pilot infrastructure like this has cut operating costs by roughly 25%, while dramatically lowering scale-up risk. Why it matters? For founders, pilot networks can reduce validation CAPEX by 50 to 70%. More importantly, cases like Global EnviroTech highlight the cost of skipping early CFD integration. That mistake alone can drive $10 to $20 million in corrective spending. For scientists and engineers, the message is blunt. Multi-scale modeling is no longer optional. CFD must inform strain selection, membrane choice, and DSP architecture from day one. Done right, it can collapse traditional 2 to 3 year tech transfer timelines. The boardroom translation. Capital allocation under physical reality. Strip away the pitch deck. This is what the capital expenditure math actually says. Cell-free systems, often presented as the scalable future of biomanufacturing, are running into a wall. And that wall is mass balance. The main story. Cell-free synthesis promises freedom from cellular burden. In practice, it overgeneralizes from small-scale success. At volumes above 10 liters, ATP and NADPH recycling efficiencies routinely fall below 60%. Enzyme denaturation and side reactions compound. Energy input rises threefold. Substrate losses of 20 to 30% accumulate across cascades. The result is unavoidable. For commodity products or high-titer targets above 50 grams per liter, cost of goods becomes 2 to 5 times higher than cellular systems. Despite more than 750 patents, commercial adoption remains limited. Mass balance explains why. Cell-free platforms shine in niche applications. High-value peptids. Rapid prototyping. Low-titer specialty compounds. But claims of universal scalability do not survive industrial physics. By contrast, cellular systems maintain roughly 80% cofactor recycling through compartmentalization, making them fundamentally more energy efficient at scale. Why it matters? For founders, this is a capital preservation signal. Avoid locking into overhyped platforms without industrial pilots. Hybrid approaches, where cell-free steps are used for pathway bootstrapping and microbes handle bulk conversion, can deliver 30% ROI improvements with far lower risk. For scientists and engineers, this sharpens experimental priorities. Focus on enzyme immobilization, cofactor regeneration, and hybrid architectures. Not every elegant system deserves to scale. The governance signal. Silent shifts that reshape feasibility. This did not make headlines. But it will change how fermentations get approved. The main story. In January 2025, the FDA released guidance on the use of artificial intelligence in regulatory decision-making for biologics. The key shift is subtle but powerful. Machine learning models can now support safety and efficacy claims, provided predictive accuracy exceeds 95%. This includes applications such as impurity profiling, viral clearance prediction, and metabolic flux simulation. The immediate effect is a 40% reduction in wet lab validation requirements for qualifying processes. Non-sterile fermentations become easier to defend when AI-based contamination risk monitoring is accepted as supporting evidence. However, this creates an asymmetry. Large companies with proprietary datasets benefit immediately. Startups without data infrastructure face higher barriers, particularly around IP protection for black box models with limited transparency. Why it matters? For founders, this can accelerate IND timelines by 6 to 12 months, directly improving valuation. But it also forces early decisions around data partnerships and consortia participation. For scientists and engineers, this unlocks AI-augmented strain and process design. Digital twins move from optional to expected. At the same time, validation discipline becomes critical. Models must be robust, explainable, and defensible. Closing signal. Taken together, this week's signals point in one direction. The future of microbial fermentation and bio-catalysis will not be defined by isolated breakthroughs. It will be defined by systems that survive stress, scale, economics, and governance simultaneously. That is the bar now. Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala, thanks for listening.